So this is our last topic for Chapter 9, talking about Le Chatelier's principle. So Le Chatelier's principle takes a system that is at equilibrium. Okay, so it's already determined where it's going to favor products or reactants. And what we're going to do with Le Chatelier's principle is we take this equilibrium, or this system at equilibrium, we're going to add a stress to it, okay, and then we're going to see how that system is going to respond in order to minimize that stress. Okay, so where is that new equilibrium going to shift in order to alleviate the stress? So let's get down this kind of definition. Alright, so we're using this word stress a lot. Okay, I wish there was another word for this, but stress really is the best way to describe it. I know you guys are under enough stress as it is, so it's a little stressful to talk about stress. But that's what we're going to be doing. We're going to be stressing out this system. We're going to be adding something to it, or sometimes taking something away in order to kind of agitate it, okay, stress it out. And then that system is going to shift in order to alleviate that stress, okay. We have 4 different stressors that we're going to talk about. We're going to talk about a change in concentration, a change in temperature, a change in pressure, which we're going to do by changing the volume, then we're going to talk about how a catalyst affects it. So let's talk about this first one. We have a change in concentration. So we're going to be dealing with one system at equilibrium for discussing all 4 of these stresses. So we're just going to be basically working with one big example. So basically what we're going to be looking at is we're either going to be shifting to the reactants, okay, or to the left, or we're going to shift to the products, or to the right, or we're going to have no shift. And those are our 3 options. So the equilibrium that we're going to consider is we're going to look at the combination of nitrogen and hydrogen, both in the gas phase, to form ammonia also in the gas phase. So let's look at our first stressor. We have our change in concentration. So what we're looking at is when we have this equilibrium, okay, we're going to pretend, well, not pretend, but basically what we kind of have is we have some sort of reaction vessel, okay, and we put a stopper in it because there's gases in there, so we want to keep those inside. Okay. And in that flask, we're going to be in equilibrium. Remember, not necessarily equal, but in equilibrium. And we're going to have nitrogen in there. We're going to have hydrogen in there. And we're going to have ammonia in there. Okay, all three gases are in this container. So what we want to look at is we want to say, all right, if we want to change our concentration, okay, well, let's do this by, say, increasing our concentration of hydrogen. Okay, we're going to add some hydrogen gas into there. Okay, what happens is now we have an overload on our left side. Okay, so we have an overload on our left side, which means in order to alleviate that overload, our equilibrium wants to shift over to our products to kind of equal that back out. Okay, so we aren't going to get to the same exact equilibrium, but if we increase this concentration here, our equilibrium is going to shift to our products to try and balance out that added concentration. So we're going to shift. I usually like to just do an arrow and say products. Okay. Basically what we're doing, why we're doing this, is we want to alleviate the addition of the reactant. Now, if we decrease the concentration of hydrogen, okay, if we are able to selectively remove some of the hydrogen from this flask, basically what happens then is we have this void in our reactant side. Okay, so we have this empty space. So some of our product then is going to shift to our reactants in order to fill in that void that we just caused. Now we can also affect our our product side, okay, because we do have product present there. So if we increase our concentration of ammonia, okay, now we're overloaded on this side. So our equilibrium wants to shift to the reactants to balance that back out. And then if we do the opposite, if we remove or decrease the concentration of our ammonia, we now have a void on this right side. We don't have enough product. So our reactants are going to shift to form some more product. All right, so that is our change in concentration. So now let's look at what happens if we change our temperature. And actually, I like to think of changing our temperature as the same thing as our concentration. So I'm going to rewrite our equilibrium. So we have nitrogen gas plus hydrogen gas in equilibrium with ammonia. Now this reaction is exothermic. So its delta H value is equal to negative 92 kilojoules per mole. So what that means, remember, we can look at our delta H value by itself, or we can include a delta H value in our reaction here. Okay, so if it's exothermic, that means it's giving off heat, which means this heat or this energy is a product. So we have plus our 92 kilojoules, or we can even just think of this as plus heat. Okay, because the value of it doesn't really matter to us. All that matters is what side of the equation it happens on. So, again, we're looking at our change in temperature. So, if we increase our temperature, okay, if we add heat to this, okay, basically how I think of temperature is if I'm adding heat, okay, if I'm adding my temperature or increasing the temperature here, okay, I'm going to think of that as increasing the concentration of my heat. Okay, now, that doesn't really make logical sense. Okay, heat is not a concentration, but it then allows us to address our shift just like we did our shift in concentration. Okay, so I'll keep this down here for comparison. If we increase our heat, okay, what we're doing is we're increasing the concentration of our product. Okay, so that's in parentheses. That's what we're doing, is we're increasing something over on this right-hand side. So if we have a heavier side over here, if we increase on this right-hand side, our equilibrium is going to shift away from that. It's going to shift towards the reactants to try and get that back balanced out. Okay, just like up here, when we increase the concentration of our ammonia, okay, which is a product, we shifted towards the reactants. And likewise, if we decrease our temperature, okay, if we say put our reaction on ice, okay, we are decreasing the concentration of our heat. In this case, we are decreasing our product. So we're going to shift to the products. Now keep in mind, if we had a different example, I'm going to do a little sidebar here. If we did a different example that was endothermic, okay, we had to add heat to it. So we'd have, say, heat as a reactant. And let's say we're going to apply that to some water. And we're in equilibrium with some hydrogen and oxygen. Okay. Now here, with this reaction, if we increase our temperature, in other words, we're increasing the concentration of our heat. In this case, with an endothermic reaction, what we're doing is we are increasing the concentration of a reactant. So now we're in the case of increasing a concentration of our reactant. Okay, so we want to shift to our products. Because in this case, we've increased our concentration of a reactant. So we want it to shift to our products to get back to that equilibrium. Okay. So keep in mind, your book doesn't really do a good job of using or really depicting the difference between exothermic and endothermic, but they're going to have opposite effects because that heat is on opposite sides. Okay, so this is for an exothermic reaction. This is for an endothermic. And we can make sure your notes are complete. We can put decreased temperature, decreasing the concentration of the heat, decreasing our reactants. So we're shifting to the reactants. All right. Our third stress that we can add to this is a change in pressure. And we're going to do that by changing the volume. So this effect is only going to address equilibriums with gases, okay? Because we're going to be changing the pressure by changing the volume, but we have to keep the temperature constant. Otherwise, we're looking at this situation. And we have to keep our concentration or the amount of gas present the same. Okay? Otherwise, we're changing our N value. Okay? So this is going to only deal with gases. And one of the rules of gases that we talked about in chapter 7 was that a mole of a gas, no matter what the gas was, is always going to occupy the same amount of space. Okay, that's how we have our molar volume. Remember that it didn't matter what the gas was. If we were at 1 atmosphere and 273 Kelvin, that gas was going to occupy 22.4 liters. Okay, so in the case of changing our pressure, changing our volume, okay, if we decrease our volume, our equilibrium wants to go towards the molar moles. Okay, or let me make sure I said that right. If we decrease our volume, okay, if we make our container smaller, we want less moles. So our equilibrium is going to shift to whatever side of the reaction has the less total moles of gas. So let's write that down. Now the opposite effect, if we increase our volume, that means we have more space. So our equilibrium wants to shift to the side with more moles of gas because more moles of gas will occupy more space. So in terms of our equilibrium that we're dealing with here, okay, on our reactant side, we have 1 mole of nitrogen gas and 3 moles of hydrogen gas. Okay. So for this equilibrium, we have 4 moles of gas in the reactant side. Then over on the product side, we have 2 moles of gas. So we're in equilibrium with 2 moles of gas in the products. So if we decrease our volume, our equilibrium is going to shift towards the side with the less moles of gas. Okay, our products are going to take up less space than our reactants. So our equilibrium is going to shift to our products. Now this is very, very dependent on this particular equation. Okay, so there are some equations that will have fewer moles of gas on the reactant side, and therefore they would shift that way. So be aware that when you talk about change in pressure by changing the volume, you have to look at the individual reaction. You can't just memorize a shift according to the decreasing. Okay. Now same thing here, we're working the same equilibrium. So if we increase the volume, we want to move towards the side with more moles of gas. Okay, our reactants have more moles of gas, so we are going to shift to the reactants. All right. Our last stress that we add to it is whether or not we introduce a catalyst. So we talked about catalysts in that TED video. And what we're actually going to find out is that a catalyst has no effect on the equilibrium. Okay, so basically it doesn't matter what the equilibrium is. If we introduce a catalyst, it will be no shift. Okay. Basically all that a catalyst does is it just speeds up the reaction. So the equilibrium isn't affected, it happens faster, okay, but there's no favoring of either side because both sides are going to be affected equally. So there's lots of QMP in your book to work through. Quite a few examples on sapling for you to practice. I encourage that you practice those. And then the lab for Chapter 9 is a online sapling lab, just working through more examples of Le Chatelier's principle. Okay, dealing with these shifts, figuring out what the stress is, which way the equilibrium is going to shift.